This video is going to cover the solutions to the tutorial problems for topic 5, what makes a car go. Problem 1. In this problem, we're asked to classify a whole lot of quantities as either scalars or vectors, and then also state their units. So let's list the vector quantities in this column, and we'll list the scalar quantities in this column. So vector quantities have a direction and a magnitude. Scalar quantities just have the magnitude. So force is a vector, and it's got units newtons, which is given the symbol capital N. Acceleration, measured in meters per second, is also a vector. Now speed is a scalar quantity measured in meters per second. Velocity is equivalent to speed except that it's got a direction as well. So it's over here in the vector quantities, and it's got the same units, meters per second. Now time doesn't have a direction, so that's a scalar quantity and it's measured in seconds. Momentum does have a direction, and there's a couple of different units we can use. We can use kilogram meters per second or Newton seconds. Distance is next. Distance doesn't have a direction, so it's a scalar quantity and it has units meters. Displacement, now that is equivalent to distance except that it's got a direction as well. So displacement is measured in meters. And finally energy. So energy doesn't have a direction. The SI units for energy are joules. So we've now done problem 1. Problem 2. We're asked to calculate the kinetic energy of a couple of things, both travelling at 100 kilometers per hour. So we'll need to use that the kinetic energy is equal to 1/2 the mass times the velocity squared. So we're told that the velocity is equal to 100 kilometers per hour. So this is equal to 100 times 1,000 meters over 60 times 60 seconds. And so this is equal to 27.8 meters per second. So now what we can do is calculate the kinetic energy of the first thing. It is a loaded truck with a mass of 10,000 kilograms. So just substituting into the kinetic energy equation up here, we've got 1/2 times 10,000 times 27.8 squared. We need to solve that on the calculator, and when we do, we get 3.86 times 10 to the 6 joules. This is giving the answer to 3 significant figures, as the data in the question is given to roughly 3 significant figures. We don't know if it's given to 1, 2 or 3, so we'll go with 3. Part B, we're then asked to calculate the kinetic energy of a car which has a lower mass. It's got a mass of 1,100 kilos. So the kinetic energy is 1/2 1,100 times the velocity squared, which is 27.8 squared again. So solving this one on the calculator, we get 4.24 times 10 to the 5 joules as our answer. Problem 3. We're asked to add the following vectors. So first of all, we're asked to add 5 meters north. So we've got 5.00, and we'll take upwards as north, plus 2 meters south. So we've got 2.00 meters back downwards. So our resultant vector goes from the tail of this vector to the head of this vector. So this is our resultant vector here. And you can see that this is going to be 5 minus 2, which is 3.00 meters, and it's upwards, so that's north. Now in part B, we're asked to add 5 meters north and 5 meters east. So once again, we draw them head to tail. So here's north going upwards, and then we're going to go east. So this is also 5.00 meters. And so our resultant goes from the tail of this vector to the head of that vector. So this is our resultant here. Now, as these are both 5 meters, this is going to be an isosceles triangle. And as that's 90 degrees up there, we know these two angles have to be equal. And so this has to be 45 degrees. So now what we need to do is work out the length of this side. In order to do that, we're going to use Pythagoras' theorem. So we've got 5.00 squared plus 5.00 squared. And calculating this on the calculator, we get 7.07 meters. So we've got 7.07 meters, and this angle shows that we're going northeast. So it's 7.07 meters northeast. And finally, in part C, we're asked to add 5 newtons south. So we'll draw that as going downwards, so that's 5.00 newtons, and 2.50 newtons east. So that's going this direction, and that's 2.50 newtons. And so our resultant goes from the tail of this vector to the head of that one. So here's our resultant. Now, as this is south and this is east, there's 90 degrees down there. So we will need to work out this angle in this case, but we can use trigonometry in order to do that. Remember that tan theta is equal to opposite over adjacent. That just comes from SOHCAHTOA. And the opposite is 2.50, and the adjacent is the 5.00, and so this is equal to a half. And so theta, in this case, is equal to 26.6 degrees. Now we also need to work out the size here, the magnitude. So in order to do that, we'll use Pythagoras again. We've got 5.00 squared plus 2.50 squared. And solving that one on the calculator, we get 5.59 newtons. So we can write this as 5.59 newtons, and then south, 26.6 degrees east. So south, and then 26.6 degrees east. So that's the solution to problem 3. In problem 4, we're asked to use conservation of energy to calculate the velocity of the cart at the bottom of the slope shown. And it rolls 2 meters down the slope, and it starts from rest. So this slope, 2.00 meters. This angle in here is 30 degrees. So conservation of energy tells us that energy is not created or destroyed, it remains the same. But to start with, when the block's up here, it's got its energy as gravitational potential energy. It has no kinetic energy as it's at rest. So we've got gravitational potential energy at top, and then at the bottom it's lost all that gravitational potential energy because it's moved down some height, h. And so that energy is converted into kinetic energy. So this is equal to the kinetic energy at the bottom. And so the gravitational potential energy at the top is given by mgh, and the kinetic energy at the bottom is given by a half mv squared. So we've got the mass on each side, so that actually cancels out. And so we can write v squared is equal to 2gh, or v is equal to the square root of 2gh. Now we know what g is, 9.8. So what we need to do now is work out this h. We've got the hypotenuse and we've got this angle in here. So according to SOHCAHTOA, we're going to need to use sine of 30 is equal to opposite, which is h, over the hypotenuse, which is 2.00. So this tells us that h is equal to 2.00 times sine 30, which is equal to 1. And so we've got this is equal to the square root of 2 times 9.8 times 1. And solving this on the calculator, we end up with 4.4 meters per second at the bottom of the slope. Problem 5. So in this problem, we're asked to draw a distance time graph. So let's draw our axes. And this is going to be time, and this is going to be distance. And we're told that a car travels along a road. It's a straight road, and the car is traveling northwards. It travels at 60 kilometers per hour for 5 minutes. Okay, so let's put the time in minutes here. So we've got 1, 2, 3, 4, 5. And for these first 5 minutes, the speed is equal to 60 kilometers per hour, which is equal to 60 times 1,000 over 60 times 60, which is equal to 16.67 meters per second. So because it's going with a constant speed, on the distance time graph, this is a straight line, and it's going to have the gradient of 16.67. So let's draw it like that. We should have this one aligned with that one. So that's for the first 5 minutes. And here we've got a gradient equal to 16.67 meters per second. So it does that for 5 minutes. And then over a 30-second interval, so that's half a minute there, it increases its speed to 80 kilometers per hour. So 80 kilometers per hour is equal to 80 times 1,000 over 60 times 60, which is equal to 22.22 meters per second. So let's first of all just worry about what happens after it's changed its speed. So it's then traveling along for 10 minutes. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with this constant speed. And so this is going to be another straight line. The gradient's going to be higher than to start with. There we go, make sure that the gradient's higher. The gradient here is equal to 22.22. And then for this 30-second time interval, it's actually increasing its speed, so it's accelerating. So this looks like a parabola on the distance time graph, which joins this gradient here to this gradient here. So that is what our distance time graph looks like. We're now asked to calculate the distance that the car travels in the first 5 minutes. So that's in here. So in order to calculate the distance travelled, it's going with a constant speed, so we can just use distance is equal to speed times time. So the speed is equal to 16.67 meters per second, and the time is 5 times 60 seconds. And so this gives us 5,000 meters, or we can put it as 5.0 kilometers. Which makes sense. If it's going at 60 kilometers per hour, then each minute is traveling 1 kilometer. And finally, we're asked to calculate the total distance traveled by the car. So we know in this first 5 minutes it travels 5 kilometers. Let's work out now how far it travels in this last 10 minutes, and then we can worry about this little bit here. So in this last 10 minutes, the distance is equal to the speed, which is the 22.22 meters per second, times the time, which is 10 times 60 seconds. And so it travels 13.3 kilometers in that time. So we would expect this to be a little over twice that, as it's twice the amount of time and it's going a bit faster. And now what we need to worry about is what distance does it travel over this time interval here. So in order to work out that distance, we can use the equation y is equal to vy naught yt plus a half at squared. We know that the time period is 30 seconds, but we're going to need to work out the acceleration. So the acceleration is equal to the change in velocity over the time, which is the final velocity, 22.22, minus 16.67 over the 30 seconds. And so solving that, we get 0.185. And so this is equal to the initial velocity, which is the 16.67, times the time, 30 seconds, plus a half times 0.185 times 30 squared. And solving that, we end up with 503 meters. So the total distance is equal to the 5 kilometers plus the 0.503 kilometers, just dividing that by 1,000 to get it into kilometers, plus the 13.3 kilometers. And so solving this on the calculator, we end up, or in your head even, we get 18.8 kilometers. And so that's the answer to part C. Problem 6. So problem 6 is a projectile motion question. In this problem, we're projecting a projectile off the top of a cliff. It's making an angle of 45 degrees with the horizontal there, and it's got an initial velocity of 15.0 meters per second. The cliff is 20 meters above sea level. And in part A of this question, we are asked to calculate the initial horizontal and vertical velocity. So just to split this down, we've got that this is 15.0 meters per second, and this is 45 degrees, and this is our initial horizontal velocity, and this is our initial vertical velocity. Now, in order to deal with this, we're going to need to use trigonometry, SOHCAHTOA. And so we know that using cos, we've got adjacent, which is the initial velocity in the x direction over the 15. So the initial velocity in the x direction is 15.0 times cos 45. And solving that on the calculator, we get 10.6 meters per second. And now we need to do a similar thing for the initial y velocity. And so in that case, we've got sine 45 is equal to opposite, which is the y, the vertical velocity, over the 15.0. And so the initial vertical velocity is 15.0 times sine 45, which is equal to 10.6 meters per second. Okay, so that's the answer to part A. For part B, we now need to calculate the maximum height above sea level. So in order to do that, we're going to need to think about what do we know happens at that maximum height. Well, at that maximum height, the vertical velocity is equal to 0. And so we can use our equation Vy squared is equal to the initial vertical velocity squared plus 2a times the height to which it's risen. And we know that this Vy squared is 0 squared. We've calculated the initial vertical velocity there, so that's 10.6 squared plus 2. Now the acceleration that is acting on this projectile is minus 9.8. It's just the acceleration due to gravity. And then this y is not the height above sea level, but it's the height above this launch height. And so solving this, we've got 19.6y, moving this term here, the second term, over to the left-hand side, is equal to 10.6 squared. And so y is equal to 5.74 meters. And so to give the height above sea level, which is what we're asked for, we need to add this 20 meters on. So this tells us that height above sea level is equal to 25.7 meters. And that's our answer to B. Now in part C, we're asked to calculate the time of flight of the projectile. So to do this, we're going to need to split this flight into two parts. Let's work out how long it takes to get to the maximum height here, and then we'll work out how long it takes to get down to the ocean down here. So time to maximum height, we can just use Vy is equal to the initial velocity in the y direction plus AT. And so we've got Vy at maximum height, that's 0, that's what we just said up here. And V0y is 10.6. The acceleration is minus 9.8, which is just g acting downwards times the time. And so this time here is equal to 1.08 seconds. So that's how long it takes to get to this point here. Now what we need to do is worry about how long it takes to get back to sea level. We know how far above sea level it starts, and we also know that it starts at rest up there. So what we can use is y is equal to y0 plus v0yt plus a half at squared. And so we're considering this part of the flight. So it starts from a height of 25.7 meters above sea level, and it ends at a height of 0 meters above sea level. The initial velocity, it's starting from up here, and the velocity there is 0. That's what we said over here. And then we've got plus a half times minus 9.8, it's being accelerated downwards, so we've got a negative times t squared. So t squared is equal to 25.7 over 4.9, and so this gives us t, which is equal to 2.29 seconds. So now to get the total time of flight, we just have to add these two times together. So 1.08 plus 2.29, and solving this on the calculator, we end up with 3.37 seconds. Okay, and then finally part D, we're asked to calculate the distance from the base of the cliff at which it lands. So that's this distance along here. So in order to do that, we just remember that it's traveling with a constant velocity in the x direction. So the distance is just equal to the speed times the time. So that is equal to 10.6 times 3.37, and solving that on the calculator, we end up with 35.7 meters. So that's how far from the base of the cliff it lands. Problem 7. So in this problem, we're told that a projectile is launched from the ground at an angle of 30 degrees to the horizontal. So that angle in there is 30 degrees, and it has an initial speed of 20 meters per second. So it's going to travel some parabolic path, looking something like this. And we're asked to calculate the range, which is this distance here, the total distance covered by the projectile. So to calculate this range here, we're going to need to know how long it spends in the air. If we know how long it spends in the air, we know that its horizontal velocity is constant, so we can then work out how far it's going to go. So let's work out how long it takes to get to this maximum height here. Let's start by doing that. Before we start, we'll just break this initial speed into the horizontal and the vertical component. So this angle in here is 30 degrees. Here we've got our initial horizontal speed, and here is our initial vertical speed. And this is 20 here. So we can use, to find the initial horizontal speed, we can use cos 30 is equal to the initial horizontal speed over 20. And so the initial horizontal speed is equal to 17.3 meters per second. And to get the initial vertical speed, we can use sine 30 is equal to the initial vertical speed over 20. And so the initial vertical speed is equal to 20 times sine 30, which is 10 meters per second. So now we know how quickly it's initially travelling upwards. We can work out how long it takes to get here, because we know here the vertical speed is 0. So in order to calculate the time, we can use Vy is equal to V0y plus AT. At this point, it's got 0 vertical velocity. The initial vertical velocity is 10. The acceleration is downward, so we've got a negative sign, 9.8 due to g times t, and so t is equal to 10 over 9.8, which is equal to 1.02 seconds. Now, the time it takes to get to maximum height is the same as the time it takes to get back to the ground. I'll leave it as an exercise for you to show that. One way to do it is to work out the maximum height and then work out how long it takes to get back from that maximum height to the ground. And so the total time is equal to 2 times 1.02, which is equal to 2.04 seconds. So now that we've got how long it spends in the air and its horizontal velocity, it's easy to get the distance. We just need to multiply them together. Distance is equal to Vox times the t, and so that is equal to 17.3 times 2.04, and solving that on the calculator, we end up with 35 meters. We just give our answer to 2 significant figures, as everything in the question was only to 2 significant figures. So problem 8. In this problem, we're given a piece of equipment called an Atwood machine. So this is basically just a pulley with 2 ropes with masses hanging off it. And this mass here, mass 1, is 2.0 kilograms, and this mass here, mass 2, is 3.0 kilograms. And in part A of the question, we're asked to write an expression for the net force on the 2 kilogram mass. It's got a tension T, and we need to take into account the weight force as well. And so in order to do this, we know that the net force from Newton's second law is equal to the mass times the acceleration. So we can write this as m1a, if we call this one here m1 and this one here m2, is equal to, now the tension is pulling it up and the weight force is pulling it down, so those are acting in opposite directions, and we need to subtract them from each other. So we've got the tension minus the weight force. So this is the expression here. Now if we want, we can substitute in. M1 we know is 2.0. We don't know what the tension is, but then we've got 2.0 times 9.8. So that is the answer to A. Part B says, write a similar expression for the net force on the 3 kilogram mass. So this 3 kilogram mass has the tension pulling it upwards and its weight force pulling it downwards. So the result of these 2 forces acting on it is going to be the acceleration of this mass. So in this case, we've got the weight force pulling it down and the tension pulling it up. And so we can substitute in the 3 kilograms. So we've got 3.0a is equal to 3.0 times 9.8 minus t. And then finally, part C says solve these equations simultaneously to calculate the acceleration of the 2 masses. So let's call this one equation A and this one equation B. If we add these 2 equations together, then we have a tension here and a negative tension here, so these are just going to cancel out. So we can add the left-hand side, so we've got 2.0a plus 3.0a, and we add the right-hand side. So we've got 3.0 times 9.8 minus 2.0 times 9.8, and then we've got plus t minus t, and that cancels out, which is why I haven't written down a t here. So we've got 5.0a is equal to, can take 9.8 out as a common factor, and we've got 3 minus 2, which is just 1. So this is 9.8, and so the acceleration is just equal to 9.8 on 5, which when we solve it on the calculator, or you can do it in your head, we get 1.96, except that we only want it to 2 significant figures, so this is 2.0 meters per second per second. So we've now solved that problem, You could have a go at working out what the tension is as well, because that is something else that could be asked. Problem 9. In this problem, we've got an ice skater who's gliding along the ice. Here they are, going in that direction there. And we're told that they're going with a constant speed of 5.0 meters per second. In part A, we're asked to draw a diagram showing the forces acting on the skater. Okay, now there is no friction in this case. If there was friction, then it would be working to slow the skater down, but she's actually traveling at a constant velocity. So what is acting on the skater is, well, there's her weight force. So let's draw that acting down like this. And then as she pushes down on the ice pushes up with an opposite and equal force, which we can call the normal force. So the skater just has these two forces acting on her, and these will cancel each other out. So part B, we're asked, what is the net force on the skater? Well, these two forces exactly cancel each other out. So the net force is 0, and that's because she is traveling at a constant speed. Any object which is traveling at a constant speed has no net force acting. So any object traveling with constant speed has no net force. So that was actually Newton's first law. Newton's first law said that an object will remain in the state of continuous constant motion unless acted upon by an external unbalanced force. Problem 10. In this problem, we have some boxes. We've got, this is mass 2, we've got M1 on top of mass 2, and we've got M3 over here, and we apply some force F here. And we're told that there's no friction along this surface, but there is friction here, so that M1 won't slide along on top of M2 and M3. So part A, we're asked to write an expression relating the acceleration and masses to the force in the diagram. So we can just use Newton's second law. We know that force is equal to the mass times the acceleration. The mass in this case consists of these three masses. This force is pushing all three of these masses. So we've got M1 plus M2 plus M3 times the acceleration. So that's our answer for A. For part B, we're asked what force is applied by M1 and M2 on M3. So this force, some of it is used up on M1 and M2, causing them to accelerate, and then they push on M3 with what remains of the force. So we can calculate that force on 3 is just going to be the mass of 3 times the acceleration. So if we want, we can get rid of this acceleration. We can rearrange this one to give that the acceleration is equal to the force over M1 plus M2 plus M3. And so the force acting on 3 is equal to Fm3 over M1 plus M2 plus M3. We've just replaced this acceleration with this term here. And this force is to the right. And then finally, we're asked what force is applied by M3 back on M1 and M2. And this is just Newton's third law, which tells us for every action there's an opposite and equal reaction. So it's the same force, Fm3 over M1 plus M2 plus M3, but in this case it is to the left. So it's pushing back this way as it's resisting the acceleration.